like I said, I'm going to be talking about declarative languages, and it's probably going to start maybe a little slow, and then I think it'll pick up. So like the first thing I want to talk about is functions, how we normally draw them, things like that. So like normally, oh well, this marker sucks. Brought a few extra ones. So if you have like x squared, right, you would normally draw it like this. And there's another way to draw it, which is if you have a set here. That marker does suck, doesn't it? So, I think this one should be good. So x squared would be a function from the set of the reals into the reals as well, right? So you put in a real, it gives out a real. But there's other functions. I don't know what the deal is with these markers. Maybe it's the board. You know, growing pains, I guess, right? Let's try through them. If this one doesn't work, I tested these all earlier today, and they all worked. Okay, that's better, right? So another way to draw them is if they're from a set that's not, that you can't draw in a line like that. Another way to draw them is like, okay, so say this is A, B, and C. You could draw a function like this, and then like that here, right? That's another way to illustrate it. And so if we have another function that's going from a set with just one element into a set with like three, how many functions could you draw from one to this three? Three, right? So here's one, and then another one would be this one, and another one would be this one, right? So if you label this element A, and this element B, and this element C, what could you name these functions? You could give them the names of the elements that they point to. So like this could be A, this could be B, and this could be C, right? Just kind of easy way to name them all. Yeah. And another kind of fun question is, so you said 3 here. How'd you get that?
Because of what's the correct term here? The number that's in, the number of options you have on the right.
Right.
Yeah.
So if you have like
multiplicity,
2 points here, and then 3 points here, how many could you draw?
6?
No. It's 2 to the third.
That's factorial, right?
No, it's 2 to the third, right? So if you have this, you could draw this function, and then you can move this one over 1, right? So now you have this one. So that's 2. And now you can move this one over 1, and then move that again. So then you have 4.
Oh, yeah.
And then if you move that, you could do the same thing.
Okay.
So the number you're going into to the power of the number you're coming from.
So I figured it was multiplication, but it's actually exponential, I see. Okay.
Mm-hmm.
Yeah.
So that's kind of one thing. And then in programming a lot, we compose functions. So does everyone know what function composition is?
Yeah, when one function contains another function?
When the output of one function is
Right.
the input of the other.
Yeah.
Right? So if we're drawing like x squared over here, right? And then say our second function is sine of x, or like sine of x plus 5 or something, it's kind of hard to see what the new function is going to be like. So if you have sine of x, and then you have x squared, you know the composition would be sine of x squared, right? But based on these pictures, you can't see what it would be like. So this notation is a little bit better for composition, because if you draw here, so if you have these two going here, and then you have another function going there, you can just trace the arrows. So let's say this function looks like this, and this one looks like this. Your new function is easy to make, right? Because you can follow here and then go there, and then there and there. So now it's easy to trace your functions if you draw them this way. So that's why we went over that. And this is better if you're doing certain types of math things, but this is better for composing. Let's see here. I wrote all these notes, and I think I have too much stuff. A few cool things. So what would your identity function be like? A function that does nothing.
A 1-to-1, like.
So if you have a set like this, going into this set, what would the identity function look like? Function that doesn't change anything.
Is it just straight across?
Yep, straight across, right? Because whatever you have on this side, if you plug this in over there, it doesn't change anything.
Yeah.
There's another cool type of function where if you compose it with itself, it's just the same function over again. So right here, so let's say you have, and then we're going to compose it with itself. So here we have one function that when you compose it with itself again, it gives you back the same function. So now we have this, and then we draw it again, and if you follow the arrows, what happens? You get the same function again. So what happens is, if all of your inputs go to one point, then your function, you can put it after itself as many times as you want, and nothing changes. There's just a few other things I want to talk about functions, and then we'll kind of get into some other stuff. Here's the handy-dandy eraser that I brought along. It's called a paper towel. You can get them at Target, CVS, wherever. Let's see here. Okay, so let's say you've got a function here from a set with 4 elements and a set with another 4 elements. Let's start writing, like naming things. So normally if you have F and you have G, the composition, people draw it like this. So now you have a new function that's called F after G, right? So what you can't do with functions is this is not the same thing as G after F, right? Because if here we did sine on the outside, you have sine x squared. The other way to do it would be sine x squared, which is not the same thing, right? So the order matters.
Yeah.
But there is a certain type of function where you can flip-flop them and it's the same thing, so the order doesn't matter. And the way to do that is if you have a partition that that changes and another partition that doesn't. So you can see here, these 2 elements change and these 2 don't. So if we call this one F and then this one G, if these 2 change and then these 2 stay the same, then you can compose F and G in any order and they don't affect each other. Does that make sense? Or should I kind of draw a little more, or is that good?
Yeah, that makes sense.
Okay, so this is cool because it lets you change the order of the elements, and then this is cool because you can do it over and over again and then nothing happens, right? So you can kind of combine the 2 and say, well, here let's do 3. Well, here let's do 3 or 5 in this one. So in this, if they all condense into one point here, but then these 2 stay the same, you could do this one over and over again, and then if you have another that switches those and leaves those 3 the same, then you could have a bunch of these, so like F, 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 and then G, and this would be the same thing as FG or GF, it wouldn't matter, right? Okay, cool. Okay, cool. Moving along. Who thought they were going to get a math lesson today? All right. Probably speed that up. Let's see here. I think I've talked about, well, there's one more thing. If you're composing from a function into itself, it's a little bit different. From a set into itself. It's a little bit different than if you're composing from one set into another. So like here, these are all one set into themselves, but if you get something like with 2 here and then 3 here, this isn't the same thing because if you call this one F, right, then you can't always compose the other way. So, I'm sorry, I made a little mistake. So if this one has 4 and this one has 3, you can't put F after F, right? Because you don't know where the other one's going to go. All right, so let's see here. I want to make sure I'm doing this right. I'm going to skip this for now. It's not very important in the rest of it, and I think it'll come to me, or maybe one of you guys will figure it out. Let's see. So one of the ways we draw things, if they're from one set into another, is we draw like dots. So let's label these sets A, B, C, and D. And what they used to look like was this, B, C, and D, right? Now I've condensed what was a set into just a dot. Does that make sense?
Represent the whole set, yeah.
Yeah, thank you. Exactly.
How do you, but relationships amongst the set, what do they signify?
Relationships among what?
Like, so obviously here you can, objects within the set or data within the set, you can
see them.
notate the relationship between it. So what's, I guess that might be what you're about to explain.
That's a great question, and that, yeah, definitely gonna explain that.
Okay,
So,
awesome.
thank you. Actually, I'm gonna say that next. So just one second. So if you have a function from A to B, you know, you can draw it however you want, right? You can do like whatever it may be. This could be a representation of it, right? And then if you have another function going here, let's call this G, then G would look like this. If you have F and G, what do we know that we have?
B? I don't know, I'm lost here.
There's one function right there.
Ah, okay, yeah.
Because given any two, you have to be able to compose them and make a third,
Yeah.
right? So let's say we also have this one. This one is not implied. But now that it is there, what else do we know is there?
B and D.
B and D, right? And the last one,
A and D.
A and D, right. All the way across. That is what you said, isn't it?
Yeah.
Okay, nice. So what's cool is with function composition, any of these are the same thing. You can do this one after this one after this one must be this big one, and this one after this one must also be the same, and then that one after this, they're all the same thing. So pretty cool. And then to get to what you said, what's your name?
Josh.
Josh, right. Okay. So earlier I talked about if you have a function from a set with just one thing in it. So you have just the one to here, and then you have those three possibilities, right? So I'm talking into a wall right now. Okay. So if this was A, B, and C, we could label these A, B, and C, right? And then I'm gonna draw these little dot structures too. And then let's say we had another set here, maybe just two elements. All right, let's say one function looks like this, right? And let's say there's another option that looks like this. I know I'm kind of crossing lines, but does everyone understand what I'm saying? There's maybe G and F there.
Yeah.
Right? So you get one arrow here, one there. This one's called F, this one's called G, right? And then this one has all three of them. A, B, and C. Does this picture make sense? That's the same thing as the first one?
Yeah.
More or less. Okay. So what's interesting here is that if you have this element, or just if you have a set here with just one element, and we said that naming these little elements here kind of implies the names of those functions, what you can do is instead of saying, all right, F applied to element A gives you some element in this set, right?
Okay.
But what's interesting is you can compose functions like this, and it gives you the exact same thing. So if you want to apply F to A, what you can do is compose function F with function A, and you will get the same element. So let's draw these. I wish I had another marker that was working. But let's say this is one function, here's another, and then this is the one, right? So all the squiggles are F, and then all the regular lines are G. Okay? F, and then G. So if we want to say, okay, what's F of A? Well, you can do this and say, okay, that's this point. Let's call this X, and this is Y. Or what you could do is say, remember this function, the existence of one in another implies the existence of the other. So if you have F here and A there, what do you know you have? F after A. So you can draw this one here. Does that make sense? So
Yeah.
this here is the same thing as this here. Because if you follow the arrows, it goes into that. So X is the same thing as FA. And you can do that with any of the other ones. So what this says is, you don't need to look at the elements anymore. As long as you have the set with only one dot in them, you can put that in the front, and you don't have to worry about what's inside them, because as long as you have those functions there, it tells you everything.
That makes good sense. Yeah, actually, it makes perfect sense. It's kind of like the same concept that's used in like object-oriented programming as well, not just declarative, right? It's like the concept of implementation, essentially.
How do you mean?
So like you don't have to understand you just have to know how to use the interface. You don't have to know how to use the implementation itself. It's the same concept.
Yeah, and so, absolutely. And so, what's interesting here is no longer do you need to know what's on the inside and say function applied to elements of sets. All you have to know is function composition in general, right? Cool. Okay, I think on to the next page. All right, we're down with one page. Good job, everybody. Let's see here. All right, so one thing to note on that same line is if this function or if this set here was like the integers or something, then you could list all the integers and that would be like the type integer, right? So if you have one dot here and these are all the integers, then all these dots in here would be all the integers, right? Or instead of doing that, you could just draw boom, boom, and say each, and list all these arrows out, and each of these would be like 1, 0, -1, and go all of them like that, right? Cool. So next thing to think about is if int is like this, you could also draw like, I don't know what languages you guys like, but like all the doubles, or like booleans, right? And if you're programming in a functional language, what you're doing is you're making up functions, right? You're saying, okay, here's a new function. It's going to be from the integers to the doubles, right? And then you declare it, and there it is. We could draw it in dots if you wanted. So the initial, boom, boom, boom.
Wait, you lost me. Is this like a top cast, or what do you mean you can integer into doubles?
I'm saying you could declare some function that goes from the integers to the doubles. So,
Okay. Yeah, I got you now.
so any function that takes an integer and adds half to it.
Okay.
So here's this 1, and then this would be int, this would be dub, and this is bool. This function we just drew there is right here. I'm sorry, I haven't done that yet. Okay? And all these they're implied, all those arrows there, and all those arrows too. Good? Okay, so now when you're writing your program, you're really just listing off a bunch of functions that go from these predefined sets. Good? And so then what you do is when you get into the REPL or something, you have all these functions, and what you can do is you apply them to a value. You would plug in 1, or you'd plug in true to some function, and then you get an answer, right? And so since these arrows are all the constants that are built into the set, what you're really doing is you've got all these functions that you've drawn when you're writing your program, and now you're in the REPL and you say, I want to evaluate some function at the value 1. So you plug in 1 and it goes here, and then it gives you some new function, right? Because that's what we talked about here. Applying a function to a value in the set is the same thing as composing on functions. And so then what you get out is a new arrow that looks like this, right? So let's say this is the chain we were following. What you're getting when you apply 1 is really this outgoing function here. That would be the answer to your program of listing all these and applying 1. Does that make sense?
Yeah.
It's kind of cool. So you can kind of think of it just everything you're writing is just chaining up a bunch of these predetermined sets that come with the programming language. They basically give you those, and then you choose a function to chain at the beginning, and then it builds them all together and then spits out the function that goes to that new constant. That's the right answer. Cool. All right, so that's kind of one part. That was like kind of one little conclusion. So does anyone have any thoughts or anything on that? Okay, cool. All right. It's nice that they have two whiteboards. I was kind of scared I'd only have one. I need some like move up and down, you know? Okay, so again, talking about functional languages, what you're doing is basically declaring a bunch of functions, right? And then saying a new one is going to be one composed with another or something like that. So a statement would be something like f is of the type integer to integer. Apparently I love the integers. And this is f of x would be equal to like 2 times x or something, right? So your program is going to be a bunch of things that look like this, more or less, right? So what we want to do, not always, but and just what I'm talking about here, is we want to name these things so we can, instead of listing off a bunch of those, you could just list off the names of them, and it condenses the program into a lot less syntax, right? So if we've already used the equal sign, so what we could do is we could say, all right, this stuff is equal to Q, right? So now if we just write Q, that's what we mean. That's the worst Q I've ever drawn, but makes sense.
Yeah.
So let's do another one. So if we have G is, well, this another end to end, and then G of X is equal to 5 plus, let's see here, am I doing this right? X, right? So this is another function, and we can name this something. We could call it P, right? So now our program, instead of having to write this and that, all we'd have to write is PQ. Good? And if this is a functional language, it doesn't matter if we write this one first or this one first, right? You can write them in either way. So PQ should be the same thing as QP. Good? What's another thing we know? If you write this again, so if you have another Q, has the program changed at all?
No, you just got 2 instances of it.
Right, so what do we also know?
But it does add the value, right? Yeah, it would.
What can we say about QQP?
It's the same as Q squared P? Wait, no, it wouldn't always be.
No. Well, yeah, that's true. Okay, it's the same thing as PQQ. If you write this one twice, what happens? Nothing different, right? So a QQP is the same thing as QP. Is that?
I'm lost there.
No, okay. So if we write, so say this is our program, you have this and then you have this. If I start writing this one again, what happens? The compiler would just ignore it. Like,
Oh, I see
it
what
doesn't
you're
mean
saying
anything.
now.
So now if you list off a bunch of 1 or a bunch of P's, you can just condense it all into QP. Good? Seeing some blanks there.
It doesn't matter how many instances that there are, the compiler looks at it the same way. It's going to reference that same instance.
Yeah.
Yeah.
Okay, so what we're saying here is the order doesn't matter. We talked about that, and you can only have 1 because having more than 1 doesn't matter. So what is it? It's a set. It's a set of all of these instances you make. Right? So really, your program is just that set notation, and then P. And then if you declare another one, what would that be? Then it would add another thing, like E or A, right? So you can look at your language or your program as just a set of all these instances. Move them around. If you add another one, it just doesn't matter at all. You can only have 1 at a time. Cool? All right. So next thing, if we have PQ, what we can also do is we can name this. And we'll call that A. right? So now instead of a letter meaning just one, it could mean two or three or anything you want, right? So now if we write A, what are we meaning? We're meaning this and that. So if we write a third one, then we could also, who wants to make up the function right now? Let's call it Z is of type bool, and a bool, and then ZX is equal to not X. I don't know, I'm just making something up. So now, if we name this, we could name it A. You guys can't see behind this printer, can you? Sorry about that. So if that's A, I'll use the same letter. Let's call this B. Alright, so now if we have B is the list of those two, and now if we write A, B, what do we mean?
PQ, QP, wait a minute, I lost myself here.
APQ?
Yep, it means all three of them,
Yeah,
right?
there you go.
And
I didn't know
so-
what, I lost the letters, but yeah.
What we could do is we could name this as well. So we could call that C. So my point is, you could list all them out, but you can also give the individual ones named, you could give any group of them a name. And then that would be talking about all the whole set of the expressions you've listed, right? Cool. So if you have more than one program, so if you got this listing, and each one is a set, if you put the two programs together, what would it be? It would be the union of the two sets, right? You guys seen union notation?
Should see you, right?
It's been a while.
Yeah, I'm right there with you.
So if you have like A, B, and C, if this is one set, and then you have the set B, C, D, what would the union be?
A, B, C, D.
A, B, C, D, that's right. Because if you're declaring a function that are all the same thing in one program, then you have another program with the same, this one, and then a new one. If you put them both together, what's the new program going to be? It's just a list of all of them, right? Cool. All right, let's see what else we've got. Okay, I think we're making progress. All right. So, given that we can write a bunch of these letters out, and then you can like kind of, if you give a value to two of them, you can write them as one, you can kind of condense them into one letter. So if you have a list of a bunch of letters from the alphabet, so like A, B, C, D, E, if each one of these can be condensed, because it can be renamed, so right, now you can write this, and then this is one letter. So this would be like F or something, and now you have C, B, and A, right? You can continue doing that until you only have one letter left. So the key of all of this is if you have a little table that tells you A, B, C, D, and then A, B, C, D, if writing one after the other, you have the answer for each of these in here, then you can just keep condensing them until you have one final answer. Have you guys seen this? You know what I'm talking about? So like this is like a multiplication table. So if you have like 1s, 1, 2, 3, 4, 5, 6, 7 over here, then the answer of multiplying them would be these numbers, right? So the only difference between this one and your multiplication is that this one has order. Doing this one before this one makes a difference. Normally. Right now it doesn't because we can change ours. But in general, it matters which one you do first. Cool? Okay, so we're gonna think about this in terms of our programming stuff right here. So one property we have is if we list all the combinations, then when you put them together, you get another combination, right? So if you have, let's see here. So if you only have the three that we have, so Q, P, and A, you could write, so you have Q, you have P, and you have A. You also have Q and P. let's name that B or something, right? And then you also have P and A, that would be C, and then you have these two, which is D. Right? And then you have all three of them, E. So this would be all the combinations, including, so this is all the combinations. Does that,
Yeah, QP, PA, and QA.
good?
Yeah.
Okay, so what we can say is if we list all of these right here, all the way through E, and then also Q and P, E, Q, P, what do we know about all of these? We know that if you compose any two of them, you're gonna get one of them again, right? Because if you do Q and P, you get B. If you do B and C, what do you get? You get E. If you do E and D, what do you get? Remember, E is all of them. You get E again, right? So every answer in here is going to be from the domain.
This is gonna sound really stupid. Can you do E and E, and it would give you E if you did?
Yeah, for
Yeah,
sure, right?
okay.
Because if E is the listing of all three of them,
Right.
if you just write them and write them again, what do you get? Same thing.
Okay.
Yeah, definitely. Okay, so now we've got this. That's called closed, right? So anytime you have a listing of these, you know that the answer is going to be one of them again. One of the possibilities, right? So if we write A, B, C, D, and E, if we don't write E, right, we know that, we don't know the answer right now, but you know it's going to be one of these 7 things. Cool? Okay. What else do we know? We know that it doesn't matter if you put parentheses here or put the parentheses here. It doesn't matter because you're gonna get the same thing anyway. Is that obvious? Does that make sense, or? Because I totally haven't explained it.
I think it makes sense. It's the way I'm thinking about it anyways.
Right, so if you write Q, P, and A, if you write them in that order, you could combine Q and P to get B, and then if you combine B with A, you would still get E. Or if you write it again and you combine these two first, you would get C, and if you combine C with Q, you still get E, right? So it means you can bracket them in any order and you still get the same answer. So a way to visualize that property is the functions we talked about earlier, right? Because function application has that same property where you can combine the first two or the second two and you still get the same thing. The way we originally drew it was we had this dot, this, and this. And if you go boom, 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 right? So if our functions are A, B, and C, you could bracket them this way, or you could bracket them this way. And they should give you the same thing, right? So this one here is represented by this function, right? So it's A and B brought together first, then composed with that one. That will give you the same thing as doing A first, and then bracketing this one. Cool?
I get what you're saying, but I don't get why it works.
It works because I think it helps to draw it this way. So if you have functions that look like this, you go, I need 4. Can I erase this part? You guys probably don't care anymore. Alright. Let's see. Bam. Then 2 are nice just because don't have to draw as many arrows. Okay, and then this one's going to be straight across. You know, there's only so many functions you can draw. What we're saying is if you compose these two and then put it before this one, you're going to get the same output as doing these two first and then putting that one in front.
So it's basically just forwards and reverse. It really, I mean, there's no other way, because you can't put the other two functions on the outside, for example, since it's composition, right?
You're saying you can't pick this one up and move it there?
Yeah.
That's
right.
correct, right?
Okay, yeah.
But if they're in the same order, you can look at these first and draw them like this, right? If you were going to combine those two, what would it look like? So you follow this one and then go up. So that one looks like this. And this one looks like this.
They're like mirrors, no?
And
I'm
then-
so lost.
So here,
If they're straight, it doesn't change.
it's the same.
I get it now,
Good.
yeah. Yeah.
And then this one, if you compose those two, you get the identity where nothing moves. And then if you put that one in front, again, nothing moves. So they're the same if you compose either way. So function composition is a good way to illustrate this property that you can bracket either way. Cool? Okay, so I'm gonna erase this now. It's funny as I see all this stuff, it's like so precious to me, but it's like, it doesn't matter. It's like, I want to erase it, but you know, you got to. Okay, let's see here. There it goes, Grant. Boom, we talked about the fact that anytime you could do one, you get an answer from the same thing, and we talked about this property that you can bracket them either way. And now remember earlier when we talked about you can arrange them in one or the other, so like if you have a function that goes 1, 2, 3, 4, remember 1, 2, 3, 4, those are arrows. You remember this? And then if you had another one that looks like, and then these two move, and those two don't, what do we say about those? Yep, you can flip-flop them, right? So function composition illustrates the property that you can bracket them either way. This property of partitioning the elements illustrates that you can flip-flop, right? So like you were asking, you can move that over there if the functions are partitioned like that. All right, and then another thing, if you're doing function composition, there's the identity function, right, which doesn't move anything. And in any set you have, you can draw the identity function because you just have, all right, so a set with 2 elements, what's its identity function? Just straight
Same
across,
thing,
right?
Yeah.
Boom. With 3 elements, it'd be the same thing. So any function, any set you have, you can draw the identity function easy. And then another thing we talked about was this like partitioning thing. If you have your partitions such that everything that moves goes into the same element, what did we say there?
Continue to do it again.
You can do it again and nothing has changed, right? Okay, so everything we've listed just now is a perfect illustration for listing your programs in functional languages. So if every function you list is just drawn as you've got a set here and then another one here. So I'm going to illustrate this function. It's got to have all the properties we just talked about. So let's draw it this way. These two condense into that first one. And now here, 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 here. I'm drawing it in front of there. All right, we'll call this one P. And then Q is going to be up here. How could I draw Q?
The opposite except for the convergence at the bottom.
Do what?
Can you do it with the convergence at the bottom?
You're saying this little set here, put it at the
Yeah.
bottom?
Yeah.
Yep. So like that, and then these 4 would go across. All right, now how can I draw this one?
All of them into one.
All of them into one? That would break one thing. What would it break? It's a good idea for sure. It'd break the partition, right?
Yes.
So what would be the problem with that? You can't move them around.
So can you have the convergence in the middle,
Okay.
like partition it in the middle, and then have
Are you saying like here, this one's on the top, this one's on the bottom? Now just have it in the middle?
Yeah.
That's right.
Here's where I'm lost on this though.
Yep.
So you have to have the same amount of data sets to be able to do that on both sides, or can we go like one down with it?
So the reason you have the same number, and this is kind of where earlier I was like, oh, I'll think about that while I'm talking, and then
Yeah.
I'll answer later. So the reason you need the same number on either side is that way you can compose them infinitely, right? If you have
Yeah.
different sets on the end and the beginning, you can't.
Gotcha.
You can't chain one after the other, right? So now you can think about your program. Every time you list a new function, you're really just putting 2 more dots at the bottom, and then making their things cross. So right, if we made up a new one, what would, like if we had some new function C over here, what would we have to do to our little model to make it right?
You just said it too. Say what you just said again.
Each function you define, you just have two more little dots, right? So we have 6 dots because we have 3 functions, and you just need to make its 2 cross and all the other ones be the same. So how do we do it?
And just add 2 more dots on each side.
Okay, so now we have 8, right? And then what? Wow, that's too small. Yeah, you do that,
Yes.
and
Still crossed in the middle? No.
let's say we have these top 6, and now we're putting the 2 at the bottom, right? Those are the extra 2. And then the extra 2.
Cross the extra 2.
Across the extra 2. And then what about the other 6?
Just straight.
Just straight, right? And then, so 6. And then, so on these other ones, we gotta make a little modification. What do we have to do?
Add 2 more,
Add 2 more. Where do they go?
the bottom and then straight across.
Bottom and straight across, right? Now there, and straight across. And then do it on all of them. So then what would the overall program be? What would the whole thing look like? If this is Q and this is P, if you're making those 2 into a program themselves, you put Q after P, right? So you're composing the functions. So what would this function composed with that one look like?
PQ.
Yep, PQ would be how you write it. How would you draw it?
Q to the right of P? Wait. Yeah, I'm lost now.
You guys have an answer.
Well, but I lost, I guess I was on the right track, but I don't know why I was thinking that.
The point of doing all these, right, is to say when you list all those out, it's the same thing as composing and putting them after each other if you draw them this way. Right? So now if you draw Q after P, it's the same thing as P after Q. You could write Q as many times as you want, you'd still get the same function. You could write P as many times as you want, still get the same function.
Ah, yeah.
So the final answer would be if you have 8 dots, right? Then you have 8 over here. If you put Q and P one after the other, this one crosses in the top, this one crosses on 5 and 6, right? So boom, man, it's killing me right now. Right there, and then this one crosses there. And what do the other ones do?
Straight across.
Straight across, right? But let's say we want to compose this one at the end. Then what happens?
The 8, the middle one there.
Yeah.
Yeah, that one, the bottom 2 cross.
Now what if we put this one on there too?
Yeah, the 3 and 4 on the left would cross.
Yep. So now they're all crossed. This is an illustration of your whole program.
Oh, there, now that makes sense. Something just clicked.
Right.
Yeah, okay.
So that's what I've got. That's all. Should put like a cloud or something around that. But yeah, if anyone has any ideas. I have a few other little what I call goodies that I can throw on there if you guys want, but that's really
It's basically like almost like a math proof of why that works, why everything
yeah.
can be composed.
It's just a nice way to picture it. It's a good way to look at it. And you know, so okay, if you're talking about like basic algebra, right? Like addition, it has a few of those properties, right? You can switch the order of them. You can put the brackets in any way. So you can draw addition like this. Right? Addition has a property where they can switch, So what is that? That's this, the partitioning, right? Addition has the associative, right? Or it has the ability you can bracket in either way, and that means you should draw it as function composition, right? So addition is function composition with these as the functions. And each number that you're adding is a new function. So lots of algebra, multiplications the same way. They all can be drawn like this. And if you look at declarative programming languages, this is the arrow diagram for them. Yeah. So one of the little goodies I wrote. This is my own. I want to bang on someone who writes programming languages to make this change. But you know, like case else expressions. If you have like if this, and then you have an else at the end. One problem with that is if you put the else at the beginning, it changes the meaning of your program, right?
Yeah.
So it doesn't have this property. You could flip the order of them. So if they would force you to write the complete set, so like if you're doing a case or an if function on like the integers, you would have to be able to say less than 0 and more than 0 and no else's. And that way, if you do that, you could flip-flop the cases and nothing would change. There's a few other things like that, but all right, I'm out of here.
Cool, thank you.